It's Flashcard Fridays at Math Science History. And since we're doing a short podcast, I couldn't think of a better topic to do than a flashcard about Albert Einstein's and Mileva Marich's Theory of Relativity. By the end of this episode, you won't need a physics degree to understand it. We're taking the scenic route in a fictional electric vehicle I like to call the Einstein-Marich EV. But first, a quick word from my advertisers. So, buckle up, plug in, and let's take a drive through space and time. Before we hit the road, let's set the scene. It's the early 1900s. Albert Einstein is married to the beautiful Mileva Marich. He's a young patent clerk in Switzerland and not yet the wild-haired global icon of genius we all know. But even then, he's already full of deep questions that keep him up at night with a lovely wife who helps him with his math. Einstein is obsessed with one thing, light. He's not the only one. The late 1800s and early 1900s were a golden age of scientific discovery. James Clerk Maxwell had shown that light was an electromagnetic wave, something that could travel through space without a medium. That baffled a lot of people. Back then, scientists thought that waves needed a medium to travel through, like sound needs air. They called it the luminiferous ether, a kind of invisible, weightless substance filling all of space. But no one could find it. Einstein, and Marich, his wife, wasn't satisfied with these explanations, and that brings us to our first stop in the Einstein-Marich EV. Einstein once said that his greatest skill was not being smarter than others, it was being willing to think differently. One of his earliest thought experiments involved a train. Imagine you're standing at a train station and a train is speeding by. On that train, a person is standing exactly in the middle of a train car. At that exact same moment, two bolts of lightning strike the front and the back of the train. To the person on the train, the lightning strike appears to have happened at the same time. But to you, standing on the platform, it looks like the lightning hits the front of the train before the back. Why? Because the train is moving forward. If something as basic as whether two things happen at the same time depends on how you're moving, what does that say about time itself? So let's switch gears and hop into our imaginary electric vehicle, the Einstein-Marich EV. It's sleek like Einstein, silent like his ex-wife Marich, and just like real electric vehicles, it moves pretty fast. But ours is special. It comes equipped with a light-speed dashboard. Now imagine two people in two separate Einstein-Marich EVs. One is parked and the other is zooming down the highway at nearly the speed of light. Both drivers turn on their headlights at the exact same moment. Here's where it gets wild. Even though one vehicle is moving, both drivers measure the speed of light coming from their headlights as exactly the same, which is 300,000 kilometers per second or 186,000 miles per second. That's the cosmic speed limit. But wait, if you're moving toward the light source, shouldn't it look like the light is coming at you faster? This paradox is at the heart of special relativity, Einstein's 1905 theory that rewrote the rules of physics. So, special relativity is built on two simple ideas. One, the laws of physics are the same for everyone, no matter how fast they are moving, so long as they're not accelerating. And two, the speed of light is constant for all observers, no matter how fast they are moving. To make these two ideas fit together, space and time can't be rigid. They must be flexible. If the speed of light doesn't change, then time must. Yep, you heard that right. Time slows down the faster you go. This is called time dilation. If you were to drive the Einstein-Marich EV near the speed of light and then come back to Earth, you'd have aged less than the people who stayed behind. This isn't just science fiction. We've tested it. GPS satellites orbiting Earth tick at slightly different rates than clocks on the ground because of relativity. And it's not just time that's stretchy. Distances contract too when you're moving fast, an effect called length contraction. To you, the road gets shorter as you speed up. All of this might sound like a glitch in the matrix, which it could be, but it is very real. So we've got special relativity down, but that only works when objects move in straight lines at constant speeds. No speeding up, no slowing down, no gravity. But gravity exists. It pulls apples to the ground. It keeps the moon in orbit, and it holds galaxies together. So, what gives? This bothered Einstein, and for the next 10 years, he worked on a new theory, a bigger one, called general relativity. And here's where he had another flash of insight. Picture yourself inside a windowless elevator, floating in deep space. Suddenly, you feel yourself pressed to the floor. How do you know whether the elevator is sitting on Earth or being pulled upward through space? Einstein realized you can't tell the difference. This led to what he called the equivalence principle. That being in a gravitational field is indistinguishable from being in an accelerating frame of reference. This was a game changer. Einstein now imagined that gravity wasn't a force like Newton thought. Instead, he proposed that massive objects like stars and planets bend space and time around them, kind of like how a bowling ball bends a trampoline. And if you put a smaller ball in the trampoline, it rolls toward the bigger ball, not because it's being pulled, but because it's following the curve. In other words, gravity is geometry. That is so cool and mind-blowing. So let's get back to our Einstein-Marich EV for a moment. You're driving on what looks like a straight road, but unbeknownst to you, the road is on a giant curved surface like a planet. Even if you're not steering, your car slowly starts to veer. Not because you turned the wheel, but because the path itself is bent. That's what gravity does to space. And that's what general relativity explains. So, how did we know that Einstein and Marich was right? In 1919, British astronomer Arthur Eddington observed a solar eclipse. During the eclipse, he looked at how stars appeared near the sun. According to Newton, their light should pass by the sun in a straight line. But according to Einstein, the sun's mass would bend space-time and curve the light just like our trampoline analogy. Eddington's team found that the stars' positions had shifted just as Einstein predicted. The result? Einstein became a global superstar. For the first time, a scientific theory had shown that space itself could be warped. So you might be wondering, okay, this is cool, but what does this mean for me? Well, it means a lot, actually. GPS wouldn't work without relativity. Satellites experience both time dilation, which is special relativity, and gravity-based time warping, which is general relativity. Your location would be off by miles if we didn't adjust for that. What about black holes? That's predicted by general relativity. What about gravitational waves? Well, first observed in 2015, ripples in space-time caused by colliding black holes was exactly as Einstein predicted. Time travel theories? All based on relativity. And yes, even your cell phone's clock owes a little nod to Einstein and his former wife, Mileva Marich. So let's pull over for a second and reflect on how Einstein, and possibly his former wife, Mileva Marich, even came up with these ideas. Well, they asked simple questions. What happens if we ride along a beam of light? They trusted thought experiments over labs. They had a group of people that gathered called the Academy Olympia, where they discussed these thought experiments. Their minds were laboratories. They looked for beauty and consistency. Einstein and Marich believed the laws of nature should be elegant and universal. They challenged authority. Just because Newton said space and time were absolute didn't mean it was true, and they embraced imagination. In fact, one of Einstein's most famous quotes is, "Imagination is more important than knowledge." So, here we are, back in our driveway, the Einstein-Marich EV powered down. You might not be driving near the speed of light anytime soon, but every time you use GPS, marvel at a solar eclipse or think about the vastness of the cosmos. You're touching the edges of a theory that forever changed how we see the universe. Einstein's theory of relativity showed us that space and time are not fixed. They're dynamic, bendable, and deeply connected. And perhaps most importantly, it reminds us that the universe still has room for curiosity, imagination, and wonder. Thank you for joining me for today's Flashcard Friday's journey through the theory of relativity with math, science, history. And until next time, carpe diem.